Hey everyone, now it's time for some normal distribution practice. First, I'm going to show you how to use mathematical notation to indicate normal distributions and standard normal distributions. And then we're going to go through some practice using what we know about the empirical rule and z-scores to estimate probabilities. Let's review some of the basics of normal distributions. Now first, remember, when we are told to assume a curve is normally distributed, we know it most likely won't be perfect. We're going to assume the population distribution is definitely normally distributed. Usually we're working with a sample and we're using our mean x bar and our standard deviation s to approximate the population mean, mu, and our standard deviation indicated by lowercase sigma. But to make assumptions using our sample about the population, we say that our curve approximates the normal distribution. We assume that if we kept taking a bigger and bigger sample, even infinitely bigger or until we get the full population, that it would eventually normalize. Let's talk about mathematical notation. We write the normal distribution in a mathematical sentence as follows: a capital X, a little tilde sign, a capital N, space, and then parentheses, our mean mu, comma, our standard deviation of the population. Again, this is how you would read this as follows. The distribution of all x values is capital X, and this approximates, that's what this symbol means, approximates a normal curve, capital N, and it is centered at our mean, mu, and it's scaled by our standard deviation of the population. This is how you would read that mathematical notation. Now look at the image to the right. All of these different curves that you see are different in height and width, but they're all normal curves. The reason for this is that you can stretch or squish a normal curve, or you can move it to be centered at a new mean. See, this green curve does not have the same center as these normal curves, but it definitely has that bell shape. All of these curves have the same bell-shaped curve operating mathematically. Using the normal curve, we can literally compare apples to oranges, knowing what we know about the normal distribution. Here's an example of literally comparing the size of apples to oranges using z-scores and approximating on the same standard distribution. We just need a key, or a Rosetta Stone, or a translator, and the process of standardization is that key. By definition, the standard normal distribution is standardized, and that means the mean is going to be set to 0, and each standard deviation will be set to 1 unit. We write this in a mathematical sentence, again using this notation. Capital Z, little tilde sign, capital N, parentheses, 0, 1. I'm going to write it again and reread how you would interpret this notation. Capital Z, the distribution of z-scores. And that approximates, again, we're using that tilde sign, about equal, it approximates a normal curve, capital N. And we will center that curve at mu equals 0. That's our mean. And it's going to be scaled by a standard deviation set to 1 unit. As a refresher, this is the equation that we use when we calculate z-scores. This is what helps us translate back and forth between any normal distribution and the standard normal distribution. Why do we do this? This helps us estimate probabilities and compare different variables to one another using the same standard scale. Let's do some in-depth review of the empirical rule and how it works. So first, let's draw a standard normal distribution in the box. And we're going to approximate the locations of the 3 standard deviations above and below the center mu. So again, remember, the standard normal distribution is the one we mathematically notate as follows. It's the distribution of all z-scores, so we write capital Z, which approximates a normal distribution, capital N, and we're going to center that distribution at the mean 0, and we're going to scale that distribution, or in other words, we're going to stretch or squish it, so that each unit is equal to 1 standard deviation. So let me draw this normal curve, and I'm sure it won't be perfectly symmetrical. Let me give it a shot. Here we're going to locate the center point of our curve. Remember, mu means mean or average, but in a normal distribution, the mean is equal to the mode is equal to the median. Here, the mean is going to be set to 0. I'm going to put 3 ticks above and 3 ticks below. And now I'm going to label these as well. 1, 2, and 3 standard deviations above the mean, mu. Now let's go below or to the left of the mean. Now remember, you can watch the other video that I will link up here and put in the description. If a z-score that we're working with isn't a whole number, we can use the Bogner-Applet to estimate. However, because of the empirical rule, we can do a lot of work just estimating probabilities using our z-scores alone. What is the empirical rule? We know that if we're looking for the area above 1 standard deviation below the mean and below 1 standard deviation above the mean, the area I'm shading here, that accounts for 68% of the area under the curve. Now, if I added the area between -1 and -2 standard deviations and +1 and +2 standard deviations, that would be 95% of the area under the curve would be shaded in. Let's add in our last standard deviation. If I added the area that's between -3 and -2 standard deviation, and I added the area between +2 and +3 standard deviations above the mean, that would account for 99.7% of the data. And we'd have about With this information, we can quickly interpret our whole number z-scores, and we can understand the probability of scoring above, below, or in between specific x values. I've switched my pen color to blue because I want to show you some more information that's very helpful. Now, if you were looking for the segment between -1 standard deviations below the mean and the mean, that area alone is 34%. If you were looking for the area between mean, 0, and 1 standard deviation above the mean, this is mirrored on the other side of the curve. If you were looking for the area between -2 standard deviations below the mean and -1 standard deviation below the mean, this area here, this small slice, is 13.6%, which is reflected and mirrored on the other side of the curve. Now this final chunk that's here, between -3 standard deviations below the curve and -2 standard deviations below the curve, is approximately 2.35%, and that's mirrored on the other side of the mean as well. We use this shorthand to be able to quickly estimate the percentages of the area under the curve between any of these standard deviations. If I asked you, what percent of the data is located between -2 standard deviations and the mean, you would want to add together the area of this slice and the area of this slice. About 48% of the area lies between these 2 points. You can do any number of combinations, adding together these individual slices between these points on your x-axis. With this information, we can quickly interpret whole number z-scores and the probability of scoring above, below, or between specific x values. Let's go through an example. A study asks a sample of millennials between the ages of 21 and 25 how much money is in their dedicated savings account. The findings indicate that the mean of this sample, X bar, is $500 and the standard deviation is $75. Let's assume that this distribution approximates a normal distribution and that X equals the amount of money in savings. First, let's write that distribution as a mathematical sentence. We've practiced with mathematical notation of these distributions, so let's repeat it. We're assuming that this distribution approximates a normal distribution. So all the possible values of X, which is the amount of money in savings, approximates a normal distribution. And remember, here we write mu, and here we write the standard deviation. Now we have been given a sample. So we will use X bar to approximate our mean, and we will use S to approximate our standard deviation. Now let me rewrite the distribution as follows. All possible values as the distribution of the amount of money in savings approximates a normal distribution in which the mean is $500, and the standard deviation is $75. Now let's draw this as a normal curve to the left, and we'll label 3 standard deviations above and below the mean with appropriate values. I know, it's a little off kilter, but that's okay. Here is our center point, which is mu, or x bar, the mean of our sample. Here we'll label this as $500. Now we want to mark 3 standard deviations above and 3 standard deviations below our mean. What is 500 plus the value of 1 standard deviation, 75? Now let's add another $75, which is another standard deviation, to this value. Awesome. Let's do this one more time to get the value in dollars associated with the 3rd standard deviation above the mean. Great. We've labeled the 1st, 2nd, and 3rd standard deviations above the mean. Now let's label the 3 standard deviations below the mean. What's 500 minus the value of 1 standard deviation? 75. Great. Let's continue. What's 425 minus 75, the value of the standard deviation? Perfect. And now let's go one more standard deviation. What's $350 minus $75? Awesome. We've now labeled 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. Now let's practice calculating probability. What is the probability of an individual having $425 or less in their savings account? What is the z-score of 425 in relation to this problem? Let's quickly sketch the area under the curve that represents this probability. First, I'm going to redraw my normal curve. Was 425 equal to a specific standard deviation on our curve? Yes. It looks like $425 is 1 standard deviation below the mean. Perfect. We're going to draw the mean here, $500. And now 1 standard deviation below the mean was $425. We're looking for the area under the curve that is equal to or less than $425. Since $425 was equal to -1 standard deviation, we know that the z-score equals -1. Now we need to know the probability that an x value would be less than or equal to 1 standard deviation below the mean. What's the easiest way to do this? Well, I know that 50% of the area under the curve is less than or equal to mu. And then I also know that we're not including this one slice between -1 standard deviation and our mean. Do you remember what the area is of this particular slice? Exactly, 34%. So I'm going to take half of the area under the curve, and I'm going to subtract this one piece of the area under the curve that we're not including. 50% minus 34% equals 16%. The probability of an individual having $425 or less in their savings account, according to the conditions of this problem, is 16%. Let's do another practice problem. What is the probability of an individual having $650 or more in their savings account? What is the z-score of $650 in relation to this problem? Quickly sketch the area under the curve that represents this probability. My curve is ugly and it doesn't matter. Again, I'm labeling mu as $500, and $650 is greater than $500. How many standard deviations away is $650 from 500? 1 standard deviation would be $575. 2 standard deviations would be $650. Exactly. We're interested in an individual having $650 or more in their savings account. So we're looking for the probability under the curve starting at $650 and increasing infinitely. So this is the area under the curve that represents this probability. How can we best calculate it? So this area here between 2 standard deviations and 3 standard deviations above the mean is 2.35%. And this tiny, tiny area above 3 standard deviations above the mean is usually approximated as 0.1%. So 2.35% plus 0.1% is approximately equal to 2.5%. Another way we could have arrived at this number is by taking 50%, this entire area above mu and underneath the curve, and subtracting the area that is unshaded between mu and 2 standard deviations above the curve. So we could have taken 50% of the area under the curve and subtracted the area between 0 standard deviations and 1 standard deviations, so minus 34%. And then we could have subtracted the area between 1 standard deviation above the curve and 2 standard deviations above the curve, which is 13.6%, which is approximately equal to 2.4 or 2.5%. So again, what is the probability of an individual having more than $650 in their savings account? It's really small, about 2.5%. Let's do our last one that showcases finding a probability between two values. What is the probability of an individual having between $350 and $575 in their savings account? What are the z-scores associated with $350 and $575 in relation to this problem? Well, again, let's quickly sketch the area under the curve that represents this probability. Our mu, which we're approximating by x bar, is $500. 1 standard deviation above mu is $575. 1 standard deviation below mu is $425. And 2 standard deviations below mu is $350. Again, we've taken 500, we've subtracted 75, we've subtracted 75 again. That's how we get to $350. Now we're looking for the probability of having between $350 and $575 in a savings account. Here we've shown that the z-score of 350 is -2 because $350 is 2 standard deviations below mu, and $575 is 1 standard deviation above mu, so z equals 1. We're interested in the probability between 2 standard deviations below the mean and 1 standard deviation above the mean, which is like saying we're looking for the probability between $350 and $575 being in a bank account. To shade that area under the curve, we're looking for the area between these 2 points. So what is the area between -2 standard deviations below the mean and 1 standard deviation above? Let's add from left to right. First, we know that the area between -2 standard deviations and -1 standard deviation is 13.6%. Next, we know the area underneath the curve between 1 standard deviation and mu, the mean, is 34%. And finally, we know that the area underneath the curve between mu, the mean, and 1 standard deviation above the mean is also 34%. When we add these 3 slices together, this one, and this one, is like saying 13.6% plus 34% plus another 34%, which equals 81.6%. So the probability of an individual having between $350 and $575 in their savings account is 81.6%. In other words, most of the accounts in the population will have a value in dollars between $350 and $575. All right, our top 3 takeaways from this video. Again, these are not comprehensive, but they're just to make sure we're on the same page. Remember, normal distributions come in all heights and widths. We can stretch them or squish them together horizontally, or we can move them around so that their means are equal to different values. However, as long as they follow the normal distribution shape, we can convert between them using a standard normal distribution. Also, number 2, remember this is how we write normal and standard normal distribution in math sentences or mathematical notation. Make sure that you memorize these. And number 3, practice using the empirical rule, adding together the sections between standard deviations on the x-axis by calculating these probabilities. All right, everybody. Great job. I'll catch you next time.